So today, as we know, and we have said in the last session, we are going to see two important topics. One is the solid biofuels and the access to clean cooking, and the other is access to electricity and the off-grid electricity data collection. That is the part that is the most complicated. So I will start today with my colleague Arnaud, and we will split the presentation in two, as you can see here in the agenda. We'll see firstly the solid biofuels and access to clean cooking, and after all the different topics for off-grid electricity and access to electricity. So we'll start to see the importance of the different topics, so the importance of solid biofuels in Sub-Saharan Africa, then the barriers and the practices to collect the data and ensure they are of good quality. And finally, we'll see a bit more about the topic of clean cooking. So what is the impact of the access or the not access to clean cooking, to families, to households, and to the people that don't have it. So I'll start now with the solid biofuels part, and then I will give the floor to Arnaud to walk you through the off-grid electricity and the access to electricity topic. So starting with the importance of solid biofuels in Sub-Saharan Africa, we know that the use of solid biofuels that here can be defined as wood and charcoal are mainly driven by cooking. So cooking is the main end use that drive the demand of solid biofuels in the region. This is because of cultural preference and the traditional use of certain cooking techniques for preparing specific meals. In rural areas as well, one reason is that the only available fuel is wood or charcoal, in the case it is produced also at the level of rural areas. So this is the accessibility problem. There is no access to other alternative fuels in rural areas, and people only can provide their energy for cooking through the use of biofuels. Instead, in urban areas, there are alternatives, but often are expensive. So there is also the affordability issue to change to clean cooking technologies and fuels. So here you can see three reasons. One is cultural, because people are used to cook with solid biofuels. There is the accessibility problem, and also the affordability problem for changing these, or barriers for changing the fuel use mostly for cooking and use more healthy and clean technologies and fuels. What are the impacts of using solid biofuels for cooking? As you know very well, when you cook with wood or charcoal, you have smoke that is released, and people that are cooking will be breathing this smoke, and this has many health consequences. Indeed, there are some estimation that more than 500,000 people die every year in Africa because of biomass cooking. And as we can see in the graph in the right, this is more than what is due to the virus of AIDS, the malaria, or tuberculosis. Also, there is other, let's say, drawbacks of cooking with biomass, and this is that picking wood takes a lot of time, mostly time of women and children. They spend a relevant part of their days collecting this wood to cook. And also there are safety concerns because they will go alone in the forest and sometimes they can be aggressed. Then there is the environmental impact. We have seen in the latest webinars that when you use biomass, there is no CO2 emission released, but this is if the use is done in a sustainable way. But in the case when the wood that is collected goes faster than the reforestation, we arrive at a point where there is no balance, so the forests start to reduce. And this has a negative impact to climate change and to the CO2 concentration in the atmospheres. What is the importance of having good biomass data for policymaking? As we have seen, we can plan objectives for clean cooking access. We can have regulation for charcoal production to improve the efficiency of the charcoal production in the country, or also to assess if the resources, forestry resources are enough, or if you are going through deforestation. So tracking biofuels data is key for countries in Sub-Saharan Africa. As you know, many of you already raised the fact that in Ethiopia, there is not yet good data collection or continuous data collection on the use of solid biofuels or complete, but there are many efforts that will be done at the national level and less international development level. I know our partners in IRENA are cooperating with the ministry and other entities in the country, I think the Central Statistic Office, to start a collection of data for biomass use in some regions of the country. So we will also follow really closely the work with IRENA, because we really think that this is a really important thing. So we will try to provide any technical input that we could. Now let's try to see some figures and see some nice ideas of what is energy, how it's consumed, and how this is evolved in the latest year. As you can see in this figure, we can see a bar chart in 1919, where most of the consumption was made by coal and wood. We can see wood was about 30% of total consumption in 1919. If you go even further in the past, wood was probably the total of the energy consumption in the world. So what happened in when the years passed and the technologies and fuel discoveries advanced? People start consuming different fuels. As you can see, we have been a transition from coal and wood to oil. We have been a transition to natural gas. We have seen also a transition to nuclear and modern renewables. The interesting thing is that, as you can see, the total consumption of food, even if in percentage or in share in the mix decreased dramatically, it has been increasing in absolute values. As you can see, in 2000, we had more wood consumed than in 1919. After that, it started decreasing slowly because developing countries start to move away from wood consumption for energy source, for energy purposes. But in the region in Sub-Saharan Africa, this is not the case, and people still use a big amount of biofuels in their energy mix. And this we will see it very soon in the next slide. Here we can see also the projection of the IEA from the stated policy scenarios. So this is the scenario of what will happen if we apply all the policies that have been publicly disclosed. We'll see that the mix will change even further going far away, but there will be still some biomass use. And this means that we have to do more to reduce the traditional use of wood than the stated policies. But we can see a bit more of that later on. So if you can see the final consumption by fuel in different regions, we easily see that in the OECD, we have a lot of oil consumption. In the non-OECD countries, there is a bit more of coal and also biofuels and waste. But if we go more in detail to Africa, we can see that biofuels and waste represent more than half of the total final consumption. And even if we go to Sub-Saharan Africa, excluding South Africa, we can see that 75% almost of the total final consumption is made of biofuels and waste. And in Ethiopia, this figure is even bigger, where we see an 88% of total final consumption made of biofuels. So this in Sub-Saharan Africa is mostly traditional biomass, but in OECD countries is different. Here we can see in this figure the split of the biofuels and waste figure that you've seen in the latest graph in green into the different products that make its total. So biofuels and waste includes primary solid biofuels, that is wood and other type of bioresidues. We have biogases, charcoal, other bioliquids like bioethanol or biodiesel, and wastes. As you can see in the OECD, we have the use of more modern kind of biofuels. We have like a 28% consumption that is made of bioethanol and biodiesel, so the one used for transportation as mixed with common gasoline and common diesel oil. Then we have some waste as well, because waste is reused in OECD country to produce energy, heat or electricity, and also some biogases, a very small percentage. But if you go to look in Africa, or even in Sub-Saharan Africa and in Ethiopia, we can see that the total of the biofuels and waste figures we have seen before, so the 75% of the total final consumption, or the 88% in Ethiopia, is practically 100% made of wood charcoal, and other bioresidues. So this is a very different picture, because as you can see in Africa, this means that almost everything is used in the traditional use of charcoal and firewood, so for cooking in inefficient ways, as we have seen before, and we will see also a bit more later. But let's try to define again what are solid biofuels. We have seen it already in some webinars before, but let's try to look at it again. Solid biofuels are organic and non-fossil material that have a biological origin, and we can distinguish primary and secondary solid biofuels. So primary biofuels, we have bagasse, that is a byproduct of the production of sugarcane. We have other byproducts from agricultural work. We have animal waste, but we also have wood, the traditional firewood, wood chips, etc. As secondary biofuels, solid biofuels, we have charcoal that, as you know, is produced by the use of wood products that goes through a kiln, a specific oven that transform the wood in this material that is called charcoal, this fuel, sorry. If you want to look how the solid biofuels that now we have defined consumption has been trending in the latest year, we can see that today, Sub-Saharan Africa represents a third of the total world solid biofuels demand. We can see also the OECD represent a much lower amount. Then we can also see that the demand since 1990 in Sub-Saharan Africa almost doubled to today. So this means that we are still increasing the use of solid biofuels, and that the access to clean cooking technologies and alternative fuels is going slower than population increase. Indeed, we can see, as is written here in the title, that population is growing by 3% per year in average in Sub-Saharan Africa. This is very fast. So the clean cooking access is not as fast as the new people that are coming to life and consuming energy for cooking or other purposes, of course. But where are solid biofuels consumed? We already said a lot about that, but how this differs between regions. We can see that in the OECD, almost half, a bit less than half is consumed in residential for heating purposes mostly, and some for cooking, but very low. Then we have a big use of biofuels in the industry for rising heat for industrial processes. While in the OECD, we see that a big chunk of it is in the residential sector. If we go to Africa and Ethiopia, we can see that almost all of that is consumed in the residential sector. And this is mostly for cooking purposes or water heating, but it's mostly cooking, as we can see. Now, if we want to look at another interesting figure, how much solid biofuels each of us consume at home. You can see a comparison between the OECD, Africa, non-OECD, Sub-Saharan Africa, and Ethiopia. We can see that OECD, in their houses, so in the residential consumption per person, each person consumes much, much less solid biofuels than in Ethiopia or Sub-Saharan Africa in general. So actually it's 5 times more in Sub-Saharan Africa than in the OECD that we consume solid biofuels. But in the OECD is also a different kind of use. This is mostly space heating and the use of modern biofuels. While in Sub-Saharan Africa, this is mostly the traditional use of biofuels such as firewood, mostly for cooking. If in this picture we add all the other energy sources used in the residential sector, we will also see another interesting trend, and that is that in the OECD, a person has access or consume much more energy than a person in Sub-Saharan Africa. As you can see, we consume in the OECD other fuels like oil, gas, electricity, etc. While in Sub-Saharan Africa, you have much less of that. This is due also to access to electricity that is very low, we will see later, but also to other reasons. What I wanted to also say is that even if we, for example, we can compare Ethiopia consumption per capita in the residential, so at home, it looks like half of the one in the OECD. This figure is even worse, because if you consider the traditional use of biofuels is really inefficient. So all this energy that is consumed is actually giving a very much lower service than the energy that is consumed in the OECD with more efficient use of biofuels, but also more efficient use of the other fuels that can provide a more useful energy output compared with a unit that is burned. So we can see that Sub-Saharan Africa we can say that is relatively poor in terms of energy and energy access for the people. We can see the same figure for cooking in specific. So what are the main fuels that people use for cooking in Africa? And we can also compare rural versus urban. This is a nice study that has been done by our IEA team on the World Energy Outlook. And we can see that Ethiopia, for example, but also in all the other countries, there is also a big difference between the urban and the rural region. In Ethiopia, for example, we see that in the urban areas, so Addis Ababa and the other bigger city, there is kind of an access to electricity and big use of electricity that is almost 30%, let's say. While in rural areas, people are mostly using fuel wood and charcoal. And this is similar to other countries, where maybe it's not electricity that's the predominance in the mix, but is LPG that is a cleaner fuel for cooking. So here we also explained how this differs depending on where you're situated in the country. So the problem is mostly in the rural areas. Now we can see something interesting and more technical, let's say, about wood. And this, but when we know how much kilos of wood are consumed or how much volume is consumed by a person through a survey, how do we know how much energy this represents? This is one of the main barriers of collecting and mostly reporting the energy use of wood. This figure or this graph represents the heating value, that is the calorific value, as we have defined it in the other webinars, of wood, depending on the moisture content, so how much humid is this wood. And the different lines depend on how this is calculated, on a dry basis or on a wet basis, or is a gross calorific value or a net calorific value. So we can see that the gross calorific value is fixed depending on moisture content, because the gross calorific value, we also include the energy that is lost by water vapor. But if you calculate the net calorific values, where we take into account the real energy that can be used while burning wood, that is not lost as water vapor, so the net calorific values, we can see how the calorific values decrease. So if we fix ourselves on the wet basis, because this is the real world, let's say, measurement, if you use wood after that is just fell or cut from a tree, it will contain more or less 55% of moisture, so of water. And these net calorific values will be around 7 megajoules per kilo. This is just an average. But if you compare it with wood that is let dry in the air for 2 or 3 years, its moisture content will be much lower at about 20%. And these calorific values will double. So with the same amount of wood in terms of kilos, we can have much more energy. And also the wood will burn much better, and the efficiency of the combustion will be, let's say, more healthy, because the smoke will be cleaner. Say that, as you know very well, in Africa and mostly in rural areas, it's difficult to store wood for 2 or 3 years, because if you leave it outside in the air to dry, it's very probable that someone will just pass by and pick it and use it for their own purposes. And here we can also see, if we also do some work on the wood, we transform it to a slightly different product like pellets, the content of moisture will also decrease again, and we'll have even a better calorific values of around 17%. So as we have said, in Sub-Saharan Africa, the wood that is mostly used is the one after felling, so with a calorific values of about 7 megajoules per kilo. And for comparison, LPG has a net calorific values of 50 megajoules per kilo, so more than 5 times higher. And let's speak now about charcoal. How do we produce charcoal? So we use firewood, input to charcoal kilns that can be of different nature or technologies, and as output, we'll have our charcoal. What are the important facts about that? Is that the calorific values of charcoal is much higher than wood, as you can see, around 30 kilojoules per kilo, but the efficiency can range a lot depending on the technology used to produce charcoal. And most of the time, this efficiency is very low in Sub-Saharan Africa if the charcoal is produced with traditional earth cleaning. The yield efficiency, that is the mass efficiency, how many kilos of food you need to produce 1 kilo of charcoal, can be as low as 10%, and in energy unit as low as 20%. But now let's try to go a bit to have an interactive session with our Menti tool. I'm gonna share now the screen on the Mentimeter. And we have a question about biofuels. Here it is. Sorry, I was not finding it. Can you see my screen? Perfect. So the question is, firstly, I let you the time to go to menti.com, and the code for these two questions we're gonna have now is 714384. So the question is, we already seen how you produce charcoal. How many kilos, sorry, of wood do you need to produce 1 kilo of charcoal in a traditional earth kiln? You think you need 2 kilos, 5 kilos, or 10 kilos? I wait 1 second or 5 seconds more to let participants answer. Now looking that many more people are connected now, that's a good news. 16 participants. 2 people answer, I'll let you the time. So www.menti.com and use the code 714384. The 2 persons that already answered said you need 10 kilos of wood to produce 1 kilo of charcoal. Now 2 people are saying that you need 5 kilos. We are speaking about traditional earth kiln. So I think both answers can be correct, depending on how good is this traditional earth kiln, is it produced well? Most people now are saying 5 kilos, but in the worst case scenario, so the worst efficiency traditional earth kiln, you will actually need up to 10 kilos. So the good answer was 10 kilos. But of course, if you have a traditional earth kiln that is a bit better, you can achieve to reduce the number of kilos you need as input. So now I can go to the next question that we have. And this is about what are the best solutions for you to achieve universal access to clean cooking. So you have to rank them from the first solution, in your opinion, to the worst, not to the worst, to the least optimal, let's say. You can take the example of Ethiopia. For you, what in Ethiopia is needed to achieve universal access to clean cooking? You need more access to LPG and LPG stove. You need more access to electricity and so electricity stoves for cooking. Or you have to provide more improved solid biofuel stoves, or you actually need a combination of all these solutions in order to achieve access to clean cooking. I'll let you some time to answer, and then I'll quickly comment, because anyway, we are gonna see some slides just after about this. Now 4 people answered, and we see that electric stoves for the moment is the first, LPG second, a combination of all solutions is second with LPG, then we have biogas digesters, and finally improved solid biofuels. So there is no correct answer here, but of course, probably the most appropriate is the combination of all these solutions, because in different areas in a country, they have different regions and different characteristics, so you cannot provide the same solution to solve the problem, and you probably need to find an adapted solution on each case. For example, where you are really far and you don't have reliable access to electricity yet, you will need to provide access to clean cooking using, for example, LPG or improved solid biofuel stoves. But when electricity arrives, of course, you can provide access by the use of electricity. So say that, I think I will continue with the presentation. we have a lot to see today, so it is better we continue. So I think it's there. Yes. Oh, perfect. So now let's try to understand why we produce charcoal out of wood. We have the good wood, but why we put it in the kilns to produce charcoal and use it instead of directly using the wood? As we have seen, you need a lot of wood and you have many losses in the production. So charcoal is a better energy product because to have the same energy as output, you need 2 kilos of wood to have the same energy as 1 kilo of charcoal. So you need double the amount in mass. So you can see here we are taking also a dry wood, so that has been drying for 2 years. If we take a wet wood that is just cut or just fell from the tree, this figure will be even worse. So we'll need 4 kilos of wood to have the same energy as 1 kilo of charcoal. So you have the same energy, but lower volume, lower weight of in the charcoal side to have the same final energy service. So it is easier to stock, to transport, and this is why we prefer to produce charcoal when it's possible. However, during the transformation, we lose a lot of energy. And traditional kiln, as we have seen, can lose as much as 90% of the energy content in the wood. So to produce 1 kilo of wood, you might need 10 kilos of charcoal, or even more, depending on the quality of the wood you're putting in, depending on also the efficiency of the earth kiln or the other kiln that you're using. So you need a lot of these trees. So you need to cut a lot of wood to produce a bit of charcoal. So this has some impacts, and mostly if you speak about climate, the impact can be on the deforestation. So losing the sustainability of the forest, of the trees growing as fast as they are used. However, if we use improved kiln, the yield efficiency can be as around 30%. So to produce the same amount of charcoal, we will need much less wood. And this is very good. So we should pay really attention and try also to track how charcoal is produced in the country, because this has a very big impact in the forests. So in the wood that is cut to produce charcoal, and if you use a better efficiency, you are doing a better job in reducing the amount of wood needed. And so you are reducing deforestation and all the impacts on the environment that this has. But let's see this even more on the real end use and the useful energy service. So cooking, the energy required for cooking with different cooking technologies and with different fuels. In this case, we'll look at wood and charcoal cooking. What is the difference? If you use a traditional stove that has about 18% of efficiency, you will need 5 kilos of wood to produce a certain meal. With the same traditional stove for charcoal that is more efficient when you use charcoal, you will need much less kilos of charcoal. You see 1.65. But to produce this charcoal, and if you are using a traditional earth kiln, you will actually be consuming 16 kilos of wood. So in the end, when you do a complete analysis, you are using more wood than when you directly combust the wood in the traditional stove. So if you see the efficiency in the life cycle assessment, we'll see that it's not 25%, but it's actually 5%, because we include also the efficiency of the charcoal kiln. If you use improved kilns, we'll see that we are really close to the wood consumed if we directly burn it. So we'll have an efficiency of around 14–15%. Now, if you use an improved stove for wood, we'll need, for the same meal, much less wood, so 3 kilos. We'll have a better combustion, so this is very good improvement in terms of the access to clean cooking, because the health related impact will be reduced, not only because we are using less wood, but also because the combustion is cleaner. So we'll see an efficiency of around 30% if you use wood and 35% if you use charcoal in improved stoves. But what is the life cycle analysis? So how much wood we need for this charcoal? You can see if we use low efficiency technologies for producing charcoal, we are still consuming a lot more wood. And so our real efficiency is only 7%. However, if we produce with improved kilns, we are going to a very much better let's say, life cycle or value chain impact. So important to mention here is that even if charcoal cooking is more efficient than wood, and is also, let's say, can be a bit healthier because the smoke that released is cleaner than the one when you use wood, the impact on wood resources and deforestation can be much, much higher, as you can see from this figure. And also the problem is that with increasing urbanization, people that go to the cities tend to use more charcoal because wood is less available, but charcoal is sold in markets, etc. So this could also, the urbanization, increase drastically the demand for charcoal. So it's really very important to track and monitor how charcoal is produced and to put in place policies for its production in order to control the efficiency of transformation and so the impact on forestry. But let's see now quickly why there is this impact on climate. So if you have a forest, our forest is absorbing CO2 emission in the atmosphere when it's growing, and it's transforming the CO2 in carbon that is stored in the wood, in the trees. After we cut some wood, we produce our charcoal and our wood for burning, for heat purposes, energy purposes, and we have some CO2 that is released. If this is done sustainably, so if we're not cutting faster or using more wood than how the forest is growing, we have an equilibrium, so no net CO2 emissions. However, if you start cutting more and more, if you're producing more and more charcoal with inefficient kilns, so we need more wood, what will happen? The forest will reduce first. We'll also burn more, so we'll have also higher CO2 release, and the absorption of the forest, since it's reduced, will be lower. So in this case, there is no equilibrium, and we have net emissions from the use of biofuels. This is an example, is a picture of two countries that are in the same island, it's Haiti and Dominican Republic. Dominican Republic has some policies on the use of wood, while Haiti didn't put it in place, and there's a different also economic characteristics. Haiti is a bit poorer in general from the Dominican Republic. So you can see that just this difference, what impact had on the forest of the two countries. Dominican Republic, we have still most of the forest in place, while Haiti has completely deforested. So putting in place good policies, give people access to other technologies, give people access also to wealth and investing in improved stoves, etc., is one of the ways to go in order to avoid environmental impact, social impact, and health impact that we have seen before. Now let's go to the interesting part to us. What are the barriers and the best practices for collecting data in the solid biofuels, for solid biofuels? So as you can see, for solid biofuels, if we focus on primary solid biofuels, this is let's say, a value chain from production to final consumption, from the left to the right. We'll have the indigenous production, import and exports can be for charcoal, of course, not many for the others. We can have transformation, for example, of food to charcoal, of food to electricity, heat, etc. And we can have a direct use, so the consumption of charcoal or wood directly in the industry residential sector. Where do we get the data here? We could either get sales data, so have, for example, a survey on people that sell wood or charcoal, for example, in markets, or companies that produce charcoal, how much they produce and how much they are selling every year. However, here we'll be losing a big part of the picture because there is a big use of this, as we know, of wood and charcoal that is not commercial. So people are picking wood in the forest and just consuming it directly. So if you only have sales data from commercial service, we are losing a big chunk of the real consumption of solid biofuel. So we will need, and the best practice will be to have a survey on the residential sector for the consumption of the fuels for cooking and other end uses purposes. What are the common barriers? As you have seen, there is this commercial, etc., commercial and non-commercial difference, but also we need to have a correct sample because there are many regional differences, as you know. So it's always good practice to cooperate with the Central Statistic Office or agency in your country before starting a data collection, because the type of solid biofuels used can be different in different regions in your country because the wood resource is different, so the forest has different trees, but also the moisture content when it's consumed is different. It's drier, it's wetter, etc. So the net calorific values will change. There are cultural differences, so different ways of cooking, for example, coffee making, or other kind of meals or related meals that are cooked with the use of solid biofuels, or also other end uses different from just cooking. Then the type of appliances available, so the access to different technologies. Different cooking stove requires a different amount of energy to produce the same meal. So we have seen that an improved stove have a much higher efficiency than a freestone stove that is a traditional one. So you will require less energy to produce the same meal. So there are many different things, so you need to cover a representative sample of your country. You have to cover both commercial and non-commercial use, as we have seen in the slide before. So the stock picking or production of charcoal and sales in the markets. We have to understand, and this we already spoke about that a lot, how charcoal has been produced. So this can estimate the real fuel wood that is being used. And now let's see a bit what are the tools that we have on how we can establish, let's say, a methodology or an action plan to track residential energy demand and specifically track the use of solid biofuels. We can have, as we say, administrative data. So we have forestry data, we have population by area. Then we can collect household surveys that gives us directly the fuel consumption by type of appliance, by type of fuels, for example, LPG stoves, how many LPG stoves have been delivered in this area, what people are using for cooking, how much wood they consume per month, per week, or per day, in order to estimate the annual consumption. We have business surveys, so how much LPG has been sold to the residential sector, how much commercial biofuels has been sold or bought. And then we have also measurement that can go with all these tools that can be, for example, when you're having a survey directly on the household, weighting the amount of fuel wood used on a day for cooking. You can also do measurement specifically for the net calorific values, so taking a sample and measuring in laboratory the net calorific values of this wood, or at least the moisture content. Then there is all this data that can go to estimation tools, because we have to, let's say, work with this data in order to give a clear picture of what is the solid biofuels consumption for the different end uses, but also what are the alternative fuels used. So you have to do some assumption, for example, what is the default consumption of a specific stove, what are calorific values, what is the energy used by each stove, etc., etc. So after doing some calculations, some assumption, you can have a complete data output on the energy consumption by source and by end use. So for example, how much wood used for cooking. And then you can create efficiency indicators, sustainable development goals indicators, like how many people have access to clean cooking technologies. Let's see a little bit more now in another slide, all these tools and how they can be used. You can see here in the columns, the different tools that we have, administrative data, household service, etc. And in their columns, and in the rows, sorry, we can see the different type of fuels. In this case, we are looking at biomass and charcoal, both in the commercial and non-commercial types. So if they are sold directly or if they are just picked. And here we tried, this of course is not perfect, to give relevance to each tool to collect each kind of data. We can see if the cell is left blank, means that, for example, forestry data are not really helpful are not the best practice to collect commercial biomass consumption. But the best practice is maybe using business surveys or household surveys. We can see that, for example, measuring directly, so weighting and sampling for the type of food is a very good practice, but of course it's costly. So this might be done only on a certain amount or on a certain sample of the study. Then we have estimation and modeling. Of course, this is modeling with just few data points, and that is what people are doing now. People are just saying, okay, we have some data from far away from a survey from 20 years ago, and population in rural areas has been increasing 3% per year. So we just assume that each person is consuming the same amount of energy as it was doing 20 years ago, and then we see the growth of energy consumption. But this is not true, because things are changing. People have access to cleaner cooking technologies. People are using different fuels. People are also changing the way they cook and they live. There are less people in one household, for example. and they're living, more people going to the cities, etc., etc. So it's really important when we do the estimation calculation to already have good quality data and complete collected. So the first option will be having surveys. As you can see, the most green things are from surveys. If you have also surveys and business surveys, you probably can cover most of the solid biofuels consumption and have a very, very good picture of what has been doing. The FAO, our partners, has been working a lot on that. They developed a methodology that is a combination of surveys and measuring to estimate solid biofuels consumption in the residential sector and other sectors. And then you could use also modeling tools with, as I say, estimation modeling tools, not projections, but for historical data, to use other qualitative data. For example, there is the database on clean cooking access by the World Health Organization that provide a percentage of households using each type of clean technology. At the national level, you have also this information from household surveys. I'm sure some of you can answer this question because you collected this data and you have available at least the qualitative data. So the answer to the question, what is the main fuel used for cooking? So it's important also to don't forget that also charcoal production should be collected and resources data, so the forest data should also be collected in order to estimate the sustainability of the use of biofuels. But now let's go a bit more on an action plan and a data collection system. How do we will start? If in 2010, for example, we had survey results, so the consumption per household by type of fuel used, we can multiply this by the number of households by type or by each region, depending on our sampling, and we can have our total consumption by different fuel for example, cooking or for other residential end uses. Then let's say that for 5 years, we didn't run any survey at all, and we just used other qualitative data coming from censuses, like the percentage of people that are cooking with firewood and charcoal, and with that, combined again with the number of households that has access to each type of fuel, and also the intensity assumption that you do in the consumption for each type of stove, if you're speaking about cooking, so how much an improved stove consumes of food to produce one meal, these are other assumptions. We can also estimate all these missing years. However, this cannot be done for a really, really long period of time, because at a point, all these assumptions start to lose their value. And we will need to plan a second data collection. So for example, in 2016, we'll run another survey and we'll collect again the data. This survey will permit us to have again observed data for 2016. We'll also permit to revise all the estimates that we had from 2011 to 2015, and as well to revise the result from an old survey. For example, the 2016 survey was done on, with better methodology, also with a higher coverage and a better sampling. It can be wise to see if the survey done in 2010 could have been improved with the information we have gathered in 2016. So it's very important to don't lose much time between different surveys. It's true it's costly, but it's more costly to don't know what is going on in the residential sector and not plan in time for alternative fuels and policies to provide people with access to clean cooking technologies and to avoid also deforestation that is related to the use of solid biofuels. If you want to speak about indicators that are interesting to analyze all these biofuels use, we can try to have a thinking split between the energy and the other activity data. When you create an indicator, it's always good to have an energy indicator, the energy part of it, so how much is the consumption, related to which activity, so to which service we are providing. For example, if you're speaking about residential, we can look at energy consumption data for cooking, water heating, space heating, and charcoal production. If we speak about solid biofuels, of course. If we're speaking about electricity, you can also look at lighting. And as activity data, the interesting parts can be the population, so how much people consume cooking per each person, how much people consume per each household. So also the number of households and dwellings, so houses that are occupied, is interesting. And if you want to go even further, the number of dwellings divided by type of cooking technologies will give also even better indicator, because with this, you could even calculate how much energy is consumed by cooking with solid biofuels, or how much energy is consumed when cooking by using LPG in an household. So depending on the level of the gas aggregation you go with data, the more the analysis you can do with your indicators. Now this is a small quiz, like I will let you answer it by yourself. It is not interactive, so you can think about the answer and then I will provide it very soon. What is the most relevant activity for an energy efficiency indicator for cooking? So you think it is better the floor area, so how much energy is consumed per square meter for cooking, or how much energy is consumed per number of dwelling or household? So the most relevant is actually the number of household, because if the house is bigger, but you're still 3 people in the house, your cooking energy needs are the same. Another, if you go even further, for cooking with solid biofuels, you want to know how much energy is consumed by cooking with biofuels in one household. You choose that dwellings are good. But is the number of total dwellings still enough? The answer is no. If we want to know that, we need to know how many dwellings are cooking with solid biofuels. So we have to exclude all the others that are using other fuel technologies. So this will give us an idea of how much biofuels is needed for cooking in one specific type of household. Now we are going to the last part of the solid biofuels presentation, and we'll see on clean cooking access, the status, the outlook, and some modeling principles. So as you know, solid biofuels in developing countries is mainly used for cooking. We have seen it very well, and is a topic that is really important for sustainable development goals. And discovered that because of all the related environmental and health and social issues that are going with it. So this covers even different targets. There is the target 7.1 that say that we need to ensure universal access to reliable modern energy service to all, and specifically the 7.1.2, that is the proportion of population with primary use of clean fuel technologies. So how we define what are clean fuel technologies? So we have different kind of ways to cook, and we can define that the not clean cooking technologies are the use of kerosene, coal, or biomass, but in traditional stoves. So biomass used in improved stoves is considered clean, as well as the use of biogas, LPG, electricity, or even natural gas. So this is the definition that we can use to calculate our indicators on how many people has access to clean energy cooking technologies. There are some complications in understanding that, because when you have also improved cooking stove and you want to estimate this energy consumption, you can have an assumption in general for all improved cooking stoves, but as you can see from here, there are many different cooking stoves, and each of them have a very different kind of efficiency, and so related CO2 emissions and related smoke in the houses. As you can see, for example, a basic improved cooking stove can reduce the smoke while cooking from about 10 to 50%, while an intermediate can reduce it from 40 to 60%, and an advanced can go up to 70% of the fuel reduction, and more than 90% in the reduction of the smoke that is released when cooking. So you can see that we have different impacts of different improved cooking stoves, but it's very difficult to know exactly which cooking stove each household is using for cooking. Besides that, there is also the other problem, that is fuel stove stacking. In a same household, you can have different cooking stoves that can be used at the same time for cooking different meals at the same time, or depending on the meals that is cooked, one person, one household wants to use a specific type of stove. So this makes the things even more complicated. At the IEA, our colleagues and also Arnaud also work on that. We try to analyze the trade-offs between the different cooking fuels and technologies, and try to give them a score instead, in terms of if it is advantages or disadvantages to use this specific technology or fuel on different criteria. So we have the cost of the stove. Of course, the biomass traditional stove is advantageous because you just need to put 3 stones, put some wood in the middle, burn it, and you put your pan on top of it. As well as for fuel costs, because you can just go and pick it up, while other alternatives are more expensive. And this is why sometimes there is a problem of affordability. Like LPG stoves are more expensive, LPG fuels need to be bought, and also its price can be variable. So there is a problem on affordability to use other kind of technologies. But then when we see health impacts, we can see that biomass, coal and kerosene, so the traditional biomass, the use of not clean cooking technologies is really the worst for the health impact of cooking. As well, the use of traditional biomass, so where there is the related picking of wood in the forests, there is also a gender inequality impact because it's mostly women that go in the woods to collect wood. Now we can go to see some analysis that the IEA World Energy Outlook team did last year on the status of clean cooking access and tracking the progress of what has been done lately. As we can see here, the global number of people that has no access to clean cooking has been stable in average in the world. However, if you look at Sub-Saharan Africa that is in green, this number has been increasing. So people without access in Sub-Saharan Africa are increasing, as we have seen before, because population is going faster than tools and frameworks that are helping to provide people with cleaner cooking technologies. As you can see that the share of people has increased from around 20% to 35% in Sub-Saharan Africa without access in the world. So 35% of people in the world without access to clean cooking are today in Sub-Saharan Africa. If you look at Africa in general, we can see that many million people, as we can see from this picture, has no access. And in the different countries, figures are of course different, but in Ethiopia, we can estimate that at least 100 million people has today no access to clean cooking technologies. But now let's see, when we want to project these figures, the clean cooking access using a modeling techniques, why we will do that? Because making projection can help us to do many things. For example, estimate the people that will have clean cooking access, and so track the SDG 7.1 indicators, but also to put some objectives. For example, if we want universal access in 2030, what are the technologies and fuels that we have to develop and deploy? And what are the policies we have to put in place? And what is the cost and the investments we need to do to achieve that? We can also try to, instead of giving a pathway for a specific objective, we can try also to anticipate what will happen if there is no change in the policies to, for example, all the health impacts, climate impacts, and environment. So we can estimate how much deforestation there will be if there are no action taken today. An example from some IEA analysis is an estimation we have done of the fuel wood consumption and the impact on the forest for 2 different scenarios. So you can see in blue and in yellow, we see the future estimated by a model on different scenarios. So the stated policies, so the policies that are being publicly mentioned, and the Africa case that goes together with the big objectives of access to clean cooking, to access to electricity, and other Africa regional specific objectives. And in gray, we can see the past, so the historical figures. In green, we also analyzed what is the impact of that on the forest area. We can see, for example, that in Nigeria, the forest area since the 1990s has been decreasing to 2018, and that the use of fuel wood has been increasing drastically. And if we don't do anything in 2040, with only the stated policies that are today, this will continue to increase. So we'll have even a bigger deforestation. However, if we follow the pathway provided by the Africa case, so to achieve the specific objectives and put in place some investments to give access to certain technologies, we could achieve a much lower consumption of fuel wood, and so a much lower impact on the forest, so on the environment and also on the health and social impact that not having access to clean cooking have. But what are the key principles to start modeling clean cooking access? As for all the other modeling that we have seen in the webinar this week with Marco, we need to start by understanding what are the drivers of our analyzed energy service. So in this case, we can have drivers for that are population, so the number of households, the number of people per household, but also, for example, the population in the rural areas and the population in the urban areas, because this can give us an idea of what the different people will be consuming later on. And then also on the cooking practices, how many numbers of meals are cooked, what is the energy needed to cook this specific meal that is cooked in this area, in this country, in this region. Then we can do some econometric analysis that we apply at the service demand. So the service demand in this case will be the useful energy that you need to cook the meal. To do the cooking, you will need a portfolio of different equipments of technologies. So we are seeing you have the traditional use of biofuels, but more cleaner alternatives like LPG or improved cooking stoves, etc., etc. So you have to do a technology fuel allocation. You have to understand, you can do a cost-based approach or you can do other different approach depending on the scenario and the models you're building to try to understand what will be the allocation of each fuels to the different households. So how many households will be cooking with LPG, how many households will be cooking with still with the traditional biomass, etc. in the future. And then by knowing the efficiency levels of each one of these cooking stoves, so how much energy each of the different technologies fuels stove needs to provide the energy required to cook a meal. And so that you can calculate the final energy demand, so the fuel that you need to burn to produce this specific energy. And so I also estimate then the energy that is required to be produced in the country. In the case of food, the wood that needs to be picked or cut. In the case of LPG, the LPG that needs to be produced in refineries or imported, for example. But other problems on doing that or other things that we need to take into account is how we actually allocate all this. Because this is not simple to say how many people will have access to a certain technology or the other. So we can know what is going on today if we have good data. So we can know how many people are cooking with clean technologies, how many people are cooking without clean technologies. And based on that, we can try to estimate the future. As I said, based on the assumption and the type of model you are using. You can have a cost-based approach. So depending on the policies that are in place in the assumption in your models, you can have different costs for the access and different fuels. If there is, for example, incentives for buying LPG and LPG stoves, maybe you can see a higher share of people with LPGs. And so you can see, after you do all this analysis, you can estimate how much people will be gaining access according to the assumption you took in your model. But now let's go a bit more to the results the IEA had applying some of these principles to clean cooking access and what are the results we got. So what the futures will look like if we don't do anything and we just apply the stated policy scenarios. The IEA model tells us that in Sub-Saharan Africa, the number of people without access will not decrease drastically. So we will not achieve full clean cooking access by 2030. That is the objective in the SDG. And I can see we did the analysis for different countries and then we allocated the total to the whole figure. So this is again because the stated policies don't provide people with the right tools to change their cooking habits. So they don't provide the tools to solve the affordability issues, the accessibility issues, and other that we mentioned before. However, in the sustainable development scenarios and in the Africa case, in the African Energy Outlook, we wanted to achieve full clean cooking access to people. So by 2030. So you see that today in Sub-Saharan Africa, we have less than 20% of the people with access, and we want to achieve 100% of the people having access in 2030. But how this is done? As you've seen, there are different technologies to do that, different fuels that are considered clean. But let's look at pictures for Sub-Saharan Africa and Ethiopia to compare. Today in Sub-Saharan Africa, as we've seen, 87% of the people lack access to clean cooking. And in Ethiopia, even more. Only 7% of the people have access to clean cooking technologies. If we look at the stated policy scenario, so if there is nothing more done than what has been claimed today by countries in terms of clean cooking policies, we'll have in 2030 still 70% of the people in Sub-Saharan Africa and Ethiopia, more or less the same figure, that are lacking access to clean cooking. However, in the Africa case 2030, the World Energy Outlook that put as objective in the model and the scenario to achieve full access, it's been calculated that the best, let's say, mix of fuels to provide access is different for different countries, of course, but it's this one. For Sub-Saharan Africa, for example, in general, we'll have a 37% provided by improved cookstoves, so still using biofuels, but with improved cookstoves, using a lot of LPG, 37%, and some other of the clean technologies that you've seen before, like electricity, etc. And Ethiopia is a bit different because the country is different. And so to achieve with the least cost access to clean cooking by 2030, in Ethiopia, we estimated that 50% of the people will need to rely on improved cookstoves for cooking with solid biofuels, that 9% will use LPG, and that 40% other clean technologies. So as you have seen, despite progress in all of these countries in terms of clean cooking, the current and planned efforts, so in the stated policy scenarios, are not enough. So we need to do more. And this is what we tried to put together in the African Energy Outlook that you can download for free and that I've shared with you in the WhatsApp group. But now let's stop speaking about solid biofuels. I hope you will have questions. I don't know if we want to answer now or later, but Arnaud will speak to you about a really, really interesting topics, that is access to electricity and off-grid data. Thank you very much for the attention.
Thank you, Gianluca. And before we shift to the second leg of energy access, which is access to electricity, we already have a question on biomass. So a question from Elias. I read it for everyone. So as the figures show that we're still consuming much amount of biofuel to fulfill our energy demand, and it will continue in the coming years, what do you advise us regarding the biofuel researchers in the country? So Gianluca, I start, and please build on what I'll answer. So very good question, Elias, indeed. As it was demonstrated by Gianluca, the use of solid biofuel is indeed prevalent in your country and in the region. I think as a researcher, maybe the first recommendation would be to try to get a better understanding of data and of the reality of biofuel use and biomass situation in the country, because as Gianluca mentioned, it's difficult to collect good, reliable data, but this is the foundation of understanding and then making good policies. And then maybe as policymakers, what we can advise if we want to limit the negative impacts of the overuse of biomass could rest on several ideas or initiatives. First, in terms of people who are cooking with traditional biomass and using solid biofuels, well, some can shift to other and cleaner fuels, like it was demonstrated, it was showed by Gianluca. In rural areas, it can be to biogas or other fuels. For those who will continue to use solid biomass, they can try to reduce the use by using more efficient devices like improved cookstoves. And then beyond looking at the users themselves, I think interesting policies can be implemented for the value chain of fuel. Gianluca mentioned a lot about how to make charcoal, but there is a lot to be done in making charcoal in more efficient ways, so to reduce the overall use of solid biomass. Gianluca, letting you building on that if you have more to say.
Thanks, Arnaud. I think your answer was complete. You mentioned the availability of good data that is, I think, the starting point for a researcher, and all the solutions that should be looked at. So I think I will not need to add anything. We can start to see the access to electricity topic. Thank you very much.
Okay, thank you. So now we'll shift to the second part of this presentation, trying to share my screen. Sorry, I have some difficulties in sharing the screen. New share. Gianluca, can you confirm me that you can see my screen?
Yes, nice, perfect. See it.
Okay, perfect. So now we'll try to take no more than half an hour to discuss access to electricity. I try to give you an overview of this topic. We'll enter then into the data collection part, reporting and indicators. And last, we'll conclude with looking ahead to the future, outlook, and how to do modeling. But before we start, let's go back to Menti for a few questions. So there is a new code to be entered. Let me know again if you can see it. So the new code is 701180. And the first question I like to ask you is, according to you, what is the electrification rate in Sub-Saharan Africa? That is to say, the share of population who has access to electricity. So we are proposing several answers from 45%, 55%, or 70%. Okay, so for now we have people answering that 45%, that is to say 500 million people have access to electricity in Sub-Saharan Africa. I give you a few more seconds to vote. Well, what's obvious is that no one is answering that 70% of Sub-Saharan African have access to electricity, which is true. And we'll see later on what the good answer is. So going to another question, entering a bit more into details. So when we look globally, we know that several regions have this issue of people without access to electricity. What we ask you to do in these questions is to rank the regions where we find the highest number of people without access to electricity. So we have proposed to use 7 regions: Asia and Africa and rest of the world. So according to you, where do we find more people without access to electricity? I give you some time because I know it's quite long to rank all those regions. So in terms of African regions, we have proposed 4 regions: East, West, Central, and Southern Africa. We have proposed India, other Asia, and rest of the world. Okay, so let's stop here. So according to you, the 4 African regions are all ranking first above India as regions with highest number of people. We'll see in a second what the status is. And what we will see is that whatever the picture is today, it is very, very different from what it used to be 10 or 20 years ago. stay on Menti because we have another question. So far we've been discussing access to electricity from households and population. Now is a question on health centers. We've heard a lot about electrified or non-electrified health centers during the COVID crisis. So the question is, according to you, what percentage of health centers in Sub-Saharan Africa do not have access to reliable electricity? Is it 35%, 60, or 75 who are lacking access to reliable electricity? Okay, so the majority of you think it's 60%. We'll see in a second, but yeah, that's the right answer according to a study that was conducted in 2018 recently. So the majority of health centers in Sub-Saharan Africa are lacking access to reliable electricity. One last question now, coming to the solutions and to the way forward to provide universal access to electricity. So here we are proposing a few solutions, and we are asking you to allocate 100 points to those different solutions. So if you are a strong believer that national grid extension is the solution and the only one, you can put 100 points on it. If you think that it's a bit of everything, you can put on a combination of these, or you can also allocate the points as you wish amongst the five options.
Sorry, no, the voting is closed.
Yes, thank you. Sorry, I just saw that. So now it's open. You shall be able to vote. So we are proposing grid and off-grid solutions. In terms of grid, we often think twofold. It can be extending national grid or densifying it. And in terms of off-grid solutions, there are also two proposed options. One is mini grids, and the other one is solar home systems. Okay, I give a bit more time for more people to vote. Let's see if a third person is giving its view on that. Okay, so we have supporter to national grid extension and solar home system first and foremost, and then to mini grid. Maybe more than densification of national grid. Of course, all these will depend country per country, but it's interesting to hear your view on that. Okay, so I don't close the voting so that if you have started, you can finish, and we will collect the results. But I'm shifting back to the presentation. Gianluca, can you confirm that you are now seeing the PowerPoint? Okay, perfect. So let's discuss access to electricity more broadly. And if we maybe zoom out and take one step behind, let's look at how electricity is impacting the world and how the use of electricity has evolved over years. So on this chart, you can see that demand for electricity has tripled in non-OECD countries, whereas in OECD countries it remained stable because it was already high. But if we look at Sub-Saharan Africa and even more at Ethiopia, we can see that the electricity output was multiplied by 12 between today and 1990. What's the reason for that? Of course, there is population and GDP increase, meaning that more people have gained access to electricity, but also those who have access to electricity are consuming more with more appliances and a higher per capita consumption. So these are the main drivers to explaining why the world is electrifying. But access is far from being universal. And in 2018, we have 860 million people without access to electricity. So maybe let's take a second to remind you, and I'm sure you are fully aware of that, but taking the time to think together why access to electricity really matter. It's been acknowledged by the international community that access to electricity is important. It's one of the Sustainable Development Goals, number 7. And we used to say that it's the golden thread that weaves together many other indicators, because energy, and I'm sure you are fully convinced of that, is the foundation of many other SDGs. Just taking a few examples, if we look at SDG 1 on poverty, we know that if we provide people without access some better solution, it will help them moving away from poverty. We have people that live below the poverty line, but still they spend a lot of their expenditure and their income in kerosene lanterns, for example, and they could invest in better lighting products like solar lanterns, which are sustainable and which are economical over time. Still on the economic side, we know that bringing reliable electricity can power new economic opportunities. And this is true when you get connection to the grid, but also when you get a solar lantern or a solar home system that enable you to open a small shop for longer because you have the light. Then when looking at another area, which is climate, we know that giving access to electricity with clean sources can displace polluting fuels like diesel that are being used in generator or kerosene. There are also impacts on water and food thanks to productive use. There are impacts on health, on education. And let's zoom a bit on education. On economic development. Here is a chart where you can see GDP in functions to electricity access rate. And what we can see is that the higher the GDP is, the higher the electrification is, but reversely and vice versa, when you increase access to electricity, this boosts wealth. So here you can see that those data might date back to 2016 or 17. So I think that the Ethiopian access rate is now higher, around 50%. But you can see that all countries are following this trend. So there is an obvious link between those two parameters. Looking at health, and that was a question in Mentimeter, 60% of health institutions in Sub-Saharan Africa are missing reliable power. And if we look at a country per country basis, it's very much dependent. So in Ethiopia, it's lower. According to this study, it's 41% with no electricity, while the remaining have access to electricity from on or from off-grid solutions. And if we look at electrification of schools, here almost half of them are without electricity. In Ethiopia, this number is bigger, according to this to the SDG 7 tracking report that the IEA contributed to produce recently. And then you have schools which have access to off-grid solutions and others to on-grid solutions. Okay, let's have a deeper look at the status of electricity access in the world. So here is the evolution of the population without access to electricity per region. You can see that in Africa, it has increased and it has peaked in 2013, which is a good news because it means that the progress that all countries realized in providing access to electricity have outpaced population growth for the first time in 2013. If we look at other regions than Africa, you will see that progress has been really faster in India and rest of Asia. Putting in another way, in the year 2000, Africa was only a third of people without access to electricity. Today, it's more closer than 80%. Or put it differently, access to electricity is increasingly an issue in Sub-Saharan Africa and no more in the rest of the developing world. And if we look region per region, you can see that there is still many people in East Africa without access to electricity, while in other regions of Africa, it also remains stable. China and India have managed to really reduce very fast the number of people without access to electricity, which means that it's possible for Africa as well to give access to everyone, because it took 35 years to China to give access to 60 million people, and for India, it took a bit more than 15 years to provide access to the same number of people. So in terms of region, and coming back to the Menti question we asked first, in the year 2000, India was the first region with people with no electricity, but this has changed. Now it's West Africa, with countries that wait a lot. For example, Nigeria, you have 80 million people without access to electricity. Central Africa is also important, with a country like DRC, same, 80 million people without access to electricity. And East Africa is still a region with quite many people without access, but the progress has been very, very fast. And here we just took Kenya, Rwanda, and Ethiopia as example, and you can see that the rate of electrification has increased a lot, by more than 20% in 5 years in Ethiopia, and subsequently the number of people who gain access in Ethiopia is estimated to be at 25 million people. So East Africa has really been leading the way on access to electricity. And we can look differently at the rates. Sub-Saharan Africa is behind other regions, but if we look again at those regions, you can see the blue line of East Africa, and you can see the really fast recent progress developed. Here, I'm going very fast on those because we will send you the presentations, but you can find all those details on our publication. And here you have a map of the continent with number of people deprived of access and the share of population they represent. Okay, now we've discussed a lot of access, but maybe we've not defined it well. So the issue with access to electricity is that there is no single internationally adopted definition. You have different technological solutions, you have different uses in terms of electricity services. So you need to do a bit of mapping of those solutions and of electricity uses. And here you have different solutions. On the left, you can find what we call pico-solar, like solar lanterns that can bring lights, that can recharge a mobile phone, that can have a radio, and these kind of devices, which are quite cheap and affordable, can provide the first energy services. Then you can climb to solar home systems, where you can provide, you can power bigger appliances like a fan, a TV. You can have more light, you can have more energy services, and it's still a standalone in-a-box product. And then you can move to the world of infrastructure. You have small infrastructures like mini grid. So here you have production capacity with solar panel, with wind turbines, for example, or micro hydro production units. You can have storage, and then you have transmission and distribution to your customers. But in the case of mini grid, it's usually to small communities or to specific customers, like a telco tower you need to power, or to a big mining company in an off-grid remote place. So you would bring power to this big anchor customer, but also to other households or other small businesses. And then you have the grid, which is a traditional way that you know very well. So At the IEA, we defined electricity access regarding households like something where you would have initial access to basic energy services, powering, for example, lights, phone charging, radio, and ability to increase. So more concretely, what do we count as an energy access solution? We count everything from the solar home system. We did not include the small solar lanterns. All those are very important because they enable poor households to start climbing up the energy access ladder. So what the international community has been doing is analyzing progress in electricity access, and we can do it in many ways. We can look at the technological solutions that helped providing access and also the fuels behind them. So here you would see a number of people who have gained access in the first 12 years of the century, and then in the following 4 years. So you can see that it's almost doubled, and the solutions to provide access to electricity have changed. You can see that there are increasingly decentralized renewables that are providing access to electricity. This is due to the technological development of solar home system, for example, of mini grids, which are quite recent. But you can also see a big part of people gaining access who got it through coal, and this is really much related to India. Because if you look more specifically at the picture in India, where, as we said, 600 million people gained access to electricity in less than 20 years, most of them gained it through the grid, and the grid was supported by coal power generation. So it's interesting to question, how did we provide to people this access to electricity? Because then when we relate to climate, it's interesting to calculate the CO2 intensity of those new connections. So as we just say, there are different solutions. Let's look maybe at all of them and see the challenges. Grid is, of course, the traditional, the most obvious solution to bring access to electricity to people who don't have it, but it is facing challenges. As we all know, power systems are already under pressure in many Sub-Saharan African countries, with losses, outages that lead people to use backup generators. So here is a study we conducted last year on the number of hours lost due to outages. And you can see that this can be an important part of an important share. In Ethiopia, we estimate it's around 5%, and it leads people to rely on backup diesel generator. And losses can be quite high as well. So it's losses in the electricity infrastructure network in developing countries are around 10%. In Africa, it's higher. And according to our analysis, in Ethiopia, unfortunately, the losses in the transmission and distribution system are even above 20%. So these are challenges that power systems are already facing. So it can bring the question on how to improve that and bring electricity to those who don't have it. And here the main questions are how to go as far as low density rural population. Would countries like Ethiopia be able to extend the lines everywhere, even if it's very far from the existing network? And another type of population which are underserved today are those living under the grid. So people who are living very close to where the grid is, but maybe they cannot afford to connect, so they are not directly connected. Mini grid are a complementary solution, but they also come with challenges. One of them is finance and economics. When mini grids are led by private sector, the math and the economics are not easy because the capex investment costs are very high. The operational costs, like operation and maintenance, are also high and underestimated. And in front of that, the revenues from users can be quite low because if you go to a village and connect with a mini grid, all those households, maybe those people have limited availability, a limited ability to pay. So when it's private sector led, the economics can be difficult. Scalability of mini-grid can be difficult. It's questionable whether we would be able to electrify 400 million people in Africa thanks to mini-grid, because projects are not standard and replication can be a long process. And then there are questions around planning. How can a mini-grid operator decide where to go and how to coordinate with the grid, so that when the grid arrives, if it arrives to that region one day, there is a good coordination. And if we look at standalone solar systems, there are also big challenges. One of them is distribution, because providing solar home system is all about a business of distribution, of having networks of sales agents, of having shops, of having repair centers. So it's a lot of human, let's say, network and infrastructure. It requires digital technologies. On the other side, it's also an opportunity to develop financial inclusions, because solar home systems are often sold under pay-as-you-go base, where people would be able to pay little by little, day after day, using mobile money. So this also requires this infrastructure. When we are looking at solar lanterns or solar home systems, these are small products which have a limited lifetime, even though it can go up to 5 or 7 years. There are questions on how to recycle those products and what to do once they are no more operating. And last, solar home systems have been mostly developed by private sector, and there are many very successful companies, including in Ethiopia, but they usually have market-based approach that cannot serve everyone. For example, in refugee camps, you are looking at a population that does not have access to electricity, and they could not afford to pay, even under pay-as-you-go, small amount day after day schemes. So that was a bit the question we asked in the Mentimeter. To our belief at the IEA and to our analysis, if we want to provide full access, we need to combine the on-grid solutions and the off-grid solutions. So to do a bit of everything depending on the situation. And here I'm just giving you the example of one country, which is Togo. You can see French because this comes from their national strategy document. So on the right, you can see the map of Togo. Togo, is in West Africa. It's a very thin country. It's 800 kilometers from north to south, and only 100 kilometers from west to east. And you already have high voltage transmission line. So you have a grid that goes north to south. But even with this grid, it's not possible to extend it to all communities who are lacking access today. And the national strategy says that they will need to rely on both grid, mini-grid, and solar home system. And basically, they are doing some innovative partnerships with private sector, with mini-grid operators, with solar home system distributor, to ensure that everyone get access to electricity, and depending on where it is. Okay, so that was the big picture of access to electricity. Let's try to enter a bit more into technical discussion around data, statistics, and reporting. So, as of today, what are the data to track electricity access rate? We basically have binary data referring to households, which means we know, is an household connected to does the household have access to electricity or not? And those binary data, they come from two main sources. One are surveys, and Gianluca and other colleagues mentioned that surveys are a very, very good source to get data, especially because you can add one question to existing surveys. And in this case, there are a lot of demographic and health surveys where some questions are asked to households regarding their source of lighting. So people will answer, I have access to the grid, I have access to a solar home system. But the challenge with surveys is that you need to carefully make your samples. Another source which is more coming from the supply side, are data which are reported by the government or the utility or the electricity agencies that will be able to provide information on the number of connections, the number of customers, the quantity of electricity provided to end users. But here again, there are some pitfalls on how you define your indicators. Is household access rate the same as coverage rate? For example, if you have a connection to a village, do you consider that all the households living in this village are connected and have access? That's questionable. So there are quite many challenges in that respect, and I come back to that in a second. So as of today, as we were saying, the definition is not internationally shared. The data are not are quite basic and binary. So, but we have many ideas to improve, and there are new initiatives for new types of data and methodologies. In terms of surveys or supply side tracking, what is being studied nowadays to improve the understanding of electricity access is to dig a bit more into the type of connection. Are people having access to electricity thanks to the grid, a mini grid, a solar home system? We can also look more into availability and reliability of the power. If you have access to the grid, how many hours do you have access to, and how many outages do you have? What's the price and how affordable is it? What's the quality of this electricity? What's the cleanness? That is to say, what's the fuel behind your electricity generation? And all these can be understood better thanks to surveys or more granular data provided by the energy companies. Another area that we can explore more is everything which is not related to households, because most research and data are focused on households, people, but not directly on health centers, public buildings, schools. And here is an area where we also need to document more and better the status of energy access. One initiative led by the World Bank aims to understand better the level of service, trying to identify if you have access to basic or more advanced services. It's not yet deployed everywhere, but it's increasingly important as a framework to consider the reliability and the nature of your access. Then looking at off-grid data, again, this space is quite new. It's been led by private sector with solar home system private companies or mini grid operators. So it's not always easy to get direct data from those operators, but it's possible. And increasingly, the association, well, the players from this sector, the industry associations are sharing more data. So it's possible to know how many solar home systems have been sold in Ethiopia or are being used. And this is something that we are increasingly consolidating with on-grid data. And just to share an initiative in Zambia, which is called the Edison platform. Here, this is something related to a public national program aiming to support off-grid development. And if you go to the Edison website, you will see some live data on the number of connections. If they come from a mini grid or a solar home system, you will have information of the quantity of electricity used by households, by institutional players. So you have these kind of new initiatives to document better off-grid data. Another way of analyzing those electricity access topics are satellite and geospatial data. So you can look at night images, at satellite images to identify solar panels, or also put together some electricity network maps and other layers of geospatial analysis. But as we said, and just to summarize on that, there are many barriers on tracking access and off-grid electricity because there are regional differences between rural and urban areas. It's not the same when you have access through solar home system or through the grid. Off-grid electricity data can be difficult to challenge. It's not always relevant, or it's not always consistent with what we are used to in the grid and the power infrastructure world. It's quite different. So calculation around access to electricity can bring some challenges. And maybe looking more at the statistical part, and I would be fast on that as well, but we have tried, Gianluca has made a very great effort to map all the data available and how to make reporting statistics on energy access. And you will see that that's not easy, but we can try to make this kind of analysis. So if we look at the different ways to provide electricity access, you have national grids, mini grid, and solar home system. And then let's have a look at the source for data collection. As we said before, you have administrative sources, you have surveys, you have measuring source. And here, I will not comment all the slide, but what you can see is that depending on the technology, whether it's grid or off-grid, not all the source, not all the methodologies are relevant. And you have pros and cons for each. For example, household surveys are very relevant to get an understanding of standalone systems use. You would know the number of people of systems installed and used, but you would miss some quantitative information, like what is the quantity of kilowatt hour used by the households. Just to give an example. And well, if we look at those information to report, you again will see that, for example, if we consider transmission and distribution losses, we know how to report that for the grid. We could try to develop some methodologies to do that for mini grid, but for standalone system, well, there are no T&D losses, so this is not relevant. So again, just to say that since electricity access covers different technologies and solutions, the indicators are not always relevant for all of them, and it needs to be adapted. Last question is, where do we report information on electricity access? So we've discussed a lot in those webinars about the energy balances, the energy tables and statistics. You know that information coming from the national grid needs to be reported on those tables. Information coming from the off-grid sector also need to be reported, but often they are missing. So mini-grid data can be easily collected if there are relations with the mini-grid operators, and in that case, it is necessary to report those data in the energy balances and statistics, but you need to specify that it's off-grid electricity. But then when you go to solar home system or solar lanterns, it's often missing, and it's difficult to put them into the energy balances. But you have other ways of reporting those data, the SDG 7 indicators or other dissemination platforms that help you capture the reality of electricity access. I just finished with a few words on how to do some modeling on access to electricity and what could be the outlook for electricity access. So, as always, when we start on modeling, the first step is to ask ourselves, what question do we want to answer with modeling? So we can have a scenario approach. We can have a deductive attitude towards future and see, okay, what will the future look like? So how many people will get access to electricity if we continue under business as usual trend? Or we can have a normative approach. So if we want universal access to electricity in Ethiopia by 2030, what is the pathway? What are the measures to implement? And this is what we have done in our Africa case scenario. Then more specific questions can be related to the number of people who have access today and who will gain access in the coming years, and all this will evolve. We can ask questions around the energy demand, like all those people who will gain access to how much electricity, how many kilowatt hours will they consume, and in regards, what will be the supply to match this demand, and which portfolio of solution will help meet this demand. We can have related questions to investment. How much will it cost to develop the capacity to serve all those people who today do not have access to electricity? And we can have, of course, questions around impacts. What will be the energy access related CO2 emissions? How many lives will be saved because people have access to electricity and to clean cooking? What will be the impact on the environment, etc. So all these are questions we can treat when doing some modeling on electricity access. Then how do we do that? At the IEA, we look at two streams. We look at the electrification projection, so how the rate of electricity access will evolve, and we look at the consumption per capita, so how many kilowatt hours someone will consume. And based on that, we estimate what will be the additional demand for electricity, and we are able to allocate it to different services, because some of this electricity will be for lighting, other will be for cooling, for water heating, for appliances. And we need to break it down to understand in a very granular way where this demand is coming from. And then in terms of power generation, what we've been doing as the IEA is to rely on geospatial analysis. So we look where people are living, where the grid is, and where it makes most sense to extend the grid or to provide solar home system or mini grid. And this is how we break it down and get data on generation and capacity for each household that will gain access to electricity. So I'm just sharing with you a few results of those modeling exercise. So here we have geospatial maps where we estimate which is the best fitted solution to bring access. These maps are available for Ethiopia as well, and Gianluca shared already with you the Ethiopia Energy Outlook, where we try to map where mini grids would be the cheapest solution and where grid extension or standalone system would be most adapted. Other results of those modeling exercises that I'm sharing very quickly with you. Let's look at how the number of people without access shall evolve in the future. So according to our analysis, Ethiopia will reach universal access before the end of the decade, so before the deadline of the SDG given by the international community. But this is not the case for other Sub-Saharan African countries. So under the current momentum and the current trends, technologies, and investment, we think that there will still be more than 500 million people without access to electricity by 2030 in Sub-Saharan Africa. But another way is really possible, and this is our Africa case. And according to those analyses, if we want every African to have access to electricity, it needs to come from a combination of on-grid and off-grid solutions. So looking a bit more at what would be the subsequent electricity demand in Africa, you can see here in our stated policy scenario that demand for electricity will increase a lot in Africa. But in our Africa case, a case where everyone has access, it will increase even more. But maybe what's interesting here is that you can break it down and to see what part of the electricity demand is coming from people who were without access before, like who will gain access to the first energy services, which part comes from people who already had access today. So this is the light green. And then, of course, you also have you can identify and isolate the electricity demand for productive uses, which is the bulk of the growth, according to our analysis. Let's look a bit at these questions around power reliability, diesel backup generator. So, according to our analysis, it's possible to decrease the transmission and distribution losses by investing in the networks, and as a consequence, the number of outages would decrease and the use of backup generator would decrease as well. So this is another result of the modeling exercise on energy access. Investment, it's another information you can get by doing this modeling exercise. Looking at two regions, developing Asia and Africa, and here again, you can see that investment need to go in the different technological solutions to provide access, grid, and off-grid. And this is my last slide, and I think it's a good conclusion of this webinar because it relates both to electricity access and to clean cooking access. It's related to greenhouse gases emissions. So today, this is the CO2 equivalent emissions coming from the use of electricity and cooking solutions for people who have access. What we've tried to do is to see, okay, if we give access to both clean cooking and electricity to everyone, what will be the impact on emissions? What will it be at the cost of the earth, of the climate, or not? And in our stated policy scenario, what we see is that since people are moving away from the traditional use of biomass, you have savings on the CO2 emissions. So you have a net change, which is quite important in terms of CO2 emissions. And if you look at our sustainable development or Africa case scenario, you can see that since everyone is getting access to clean cooking, we have expanded the use of LPG. You also have emissions that come from more grid power generation. Some come from renewable, but some come from fossil fuels. If you do the life cycle analysis, you would see that even a solar home system is generating emissions. So bringing access to cooking and electricity creates emissions. But if all those who are today using traditional biomass move away from that, you have savings in terms of CO2 and methane emissions that are net, and you are really saving emissions. So the key message here is that on top of all the other advantages of bringing access to energy, so both cooking and electricity, in terms of economic development, in terms of health, on education, and other, you have a net climate benefit with a net reduction of the GHG emissions.